All right, I want to talk about, or continue talking about chemical reactions. Experiments 17 and 18 deal with chemical reactions, so I want to discuss these before we do the experiment. And so we're looking at HCl. HCl is soluble in water. Normally it's a gas called hydrogen chloride gas, but a lot of acids are soluble in water. Solubility, is that a physical property or a chemical property? It's a physical property because when you dissolve it in water, it's still HCl. So that's a physical property. HCl is a strong electrolyte, weak electrolyte, or non-electrolyte? Now, it's a strong electrolyte. Now, there are two definitions for electrolyte. Definition one is, does it break apart? And HCl breaks apart. It breaks apart into H plus and Cl minus. So we have the aqueous ions. That's a physical property or a chemical property? Ionization like this. Physical? Chemical? So chemical property, one way we can just differentiate between a physical and a chemical change is that in this change, is it still HCl or do we have to label it differently? Once it breaks apart, do we have to put a different label or name to it? Or is it the same name, just hydrochloric acid?
I don't know because you have to add the charging, but it's kind of still the same.
Well, were the charges over here? I mean, what's the charge on Cl?
Minus.
Yeah, it's like this. Sodium chloride, there's no charges there, but are there charges there? There's no net charge, but individually the ions show charge. Sodium would be +1, Cl would be -1, and we call it sodium chloride. Well, the same thing here. I mean, there's no charge because it's neutral, but the charges are there because it consists of these two species in solution. However, one thing is H plus. H plus is very unstable. H plus is the smallest of the group 1 cations. The next biggest would be lithium. Lithium ion Li plus is huge compared to H plus. Why? Well, lithium has 3 protons, and then it has one what we call core electron. Well, actually, not one, 2 core electrons. And then it has a valence electron. The valence electron has been ionized. And so lithium plus would have the 3 protons in the nucleus and then either 3 or 4 neutrons. I know that because lithium forms lithium-6 and lithium-7 is the common isotopes. Just remember it from a homework problem. But here we'll have 2 electrons in the 1s orbital. Well, how does that compare to a hydrogen ion? Hydrogen ion has no electrons and just a single proton in the nucleus. How big is the nucleus? 1/10,000th of an atom. And so this is huge compared to this. In fact, hydrogen ions are so unstable, you can't have hydrogen ions dissolved in water. What's going to happen are the hydrogen ions are going to be attacked by water right away, or hydrogen ions will attack water. There are 2 ways of thinking about this. One way of thinking about this is Bronsted. Acids are what in Bronsted? Did I talk about acid bases? Yeah, Bronsted acid is a proton acceptor or proton donor? Proton donor. So one way of thinking about it is a proton is donated to water. Well, nothing's really donated, it's there. So the proton goes to water. Whereas a Lewis, we think of it differently. In terms of Lewis, how do we think of acid-base reactions? Yeah, electron pair acceptor. And so for Lewis, I like to do this. We have an electron pair here, and that's going to attack the proton here. And so in Lewis, electron pair acceptor is the acid, electron pair donor is the base. So in Lewis acid-base reactions, we like to think of the base attacking the acid with its electron pair. Why would this electron pair attack the acid, H plus in this case? So let's take a look. What is the oxidation state of oxygen? -2. Oxidation states, I'd like to write in parentheses, -2. What is the formal charge on that oxygen? Not -2. Do you guys remember how to do formal charge and oxidation states from the Lewis structure? Oxidation state, you assume what? That the bond is shared 50-50, or the bond is winner take all? Winner take all. So who's the winner? And oxygen takes all. It takes all the electrons that are being shared. So it takes all these. How many electrons does it end up with? 8. How many does it normally have? 6 valence electrons. So it ends up with 8, normally has 6, so it has 2 extra electrons. Those 2 extra electrons give an imbalance of positive and negative charge, and we end up with a -2, because we have 2 extra electrons. Each extra electron is -1. Does that make sense? This? And so -2 is its oxidation state. Formal charge, we make a different assumption. In formal charge, we assume that what? It's 50-50. Now, lone pair is not shared, so there's no one to split this with. It's only the bonding pairs that are split. And so there are 2 electrons in the bond. One electron goes to hydrogen, the other electron goes to oxygen. 2 electrons in this single bond. So each line represents 2 electrons, or 2 dots. Now how many dots does oxygen end up with? 6. How many is it supposed to have? So it broke even. In other words, there's a balance of positive and negative charge, which means its formal charge is 0. So the formal charge is 0. Formal charges in oxidation states are 2 different things. And so this is why you have to identify them differently. This is why for oxidation states, I always write them in parentheses. We compare oxidation states with other oxidation states. Formal charge, I circle. We compare formal charges with other formal charges, but we never cross-compare them. So it wouldn't be fair to compare an oxidation state with a formal charge. It would be like asking, what is the biggest apple? And then you tell them the biggest orange is this, but you didn't ask about oranges. You asked about apples. And so it just doesn't make sense to compare apples and oranges. And so going back over here, what is the formal charge on oxygen? 0. Now, is that bond 100% ionic, winner take all? Does water form 100% ionic bonds? Here I need to talk about what forms ionic bonds. Ions, too. Typical ions are metals and nonmetals. Those form ionic. Molecular compounds don't form ionic bonds. You know what type of bonds molecular compounds typically form? Covalent bonds. Water is a molecular compound. It's going to form covalent bonds. Now, we have something that's like, it's called 100% covalent. 100% covalent is 50-50 sharing. So this is not 100% ion, but this is also not 100% covalent. Do you know what we call an oxygen-hydrogen bond? We call that polar covalent. What does polar covalent refer to or mean? Polar covalent. Have you heard that term before, polar covalent bond? It means
Covalent refers to like the bonds themselves, and polar is it being pulled in any direction or is it balanced?
yeah. Covalent means sharing. Ionic means no sharing. Polar covalent means unequal sharing. And so this is a polar covalent bond, means it's unequal. Which one is stronger, oxygen or hydrogen, in terms of electronegativity? Oxygen. And so what happens is this pulls the electrons towards itself, but it can't completely pull it away. So the way I think about it is it's a tug of war. Oxygen is stronger, but hydrogen does not completely lose. If hydrogen completely lost, then it would be ionic. We have something called delta En to give us an idea. Delta En, do you know what that stands for? Delta En. This gives us an idea of how ionic or how covalent the bond is. So delta En of 0 is 100% covalent. That is, if you have a tug of war, and the tug of war was between two equal, like hydrogen versus hydrogen, who wins the bonding electron? It's a tie. Oxygen versus oxygen, who wins? It's a tie. But oxygen and hydrogen, who wins? Oxygen, because oxygen is more electronegative. So delta En 0, delta En 0, delta En, well, oxygen is 3.5, hydrogen is 2.1. And so we have some numbers. Like if the delta En is 0, we call it 100% covalent. If the delta En is above 2, 2.5 or so, then we call it ionic, like 100% ionic. It's an uneven thing. So this bond is not 100% ionic, and therefore -2 is not 100% accurate. This bond is not 100% covalent, so 0 is not 100% accurate. But these are nice because these tell us the extremes. And the reality is it's somewhere in between these two extremes. Do you know exactly where? No, I don't know exactly where, but we don't need to. We're just going to call it somewhere in between. And how do we do that? How we do that is we use a symbol, delta minus. I don't know what the exact number of delta is. It's negative something, somewhere in between the extremes. Does that make sense? Have you guys used delta minus and delta plus?
A little bit.
So the oxygen is going to be delta minus. That means the hydrogen is going to be delta plus. The hydrogen is between 0 and +1. And this hydrogen is going to be delta plus here. And so what we have here is we have this. This oxygen being minus likes positive things. And so this oxygen will want to attack this H+. And it attacks it with a lone pair. So this is the base, and it's a lone pair donor. And what we're going to form is we're going to form what? Hydronium. Yeah. Hey, this is H3O plus. H3O plus, where do I get the positive charge from? Where does this positive charge come from? Is it missing? Doesn't look like it. I mean, how many electrons did I start with here? 2, 4, 6, 8. 2, 4, 6, 8. Looks like I have all the electrons. Why is it positive? I got the octets. We got the octet here. It's because of how the electrons are distributed. And so if we look at the oxidation states, nothing changed with the oxidation state, but something did change with the formal charge. The oxidation state of this oxygen, winner take all. If winner take all, 2, 4, 6, 8, the oxidation state is minus 2. So the oxidation state, nothing changed. What changed was the formal charge. What's the formal charge on this oxygen? Can you do it in your head? Or if you can't do it in your head, draw it.
Well, if it has an extra, does that mean it's minus 1 or plus 1?
If it has an extra electron, it's minus. If it has an extra electron, it's minus. But it has an extra proton. So oxidation state, winner take all. How would I box this?
You put all of the bonds in the one pair with the oxygen.
Right. For formal charge, how would I do this? All right, I cut all the bonds in half. What about this lone pair? Do I split the lone pair in half and share it with empty space? No. And so how many electrons does oxygen end up with? So this is something I do in my head. 1, 2, 3, 4, 5. How many is it supposed to have? 6. So it's missing 1 electron. It's missing 1 negative charge. If it's missing 1 negative charge, then there's an imbalance of charge. And it's going to end up as plus 1. And so the oxidation state of this is plus. Well, what I want to do is I want to add another proton to this. You see, I have a lone pair here. And I want to donate that lone pair to this H+. So hydronium will attack this H+, and it'll form H4O, H4O 2+. Successful, or what do you think? Will this attack another proton? Because I got another lone pair here. Will this attack another proton? Yes or no? Just give me your best guess. No? 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 Maybe? Everybody says no. Why?
Oxygen really hates being like a plus.
Yeah.
Plus 2.
Right. Plus, plus, are they going to come together? No. So it stops here. It doesn't go any farther. H3O plus is not going to attack another hydrogen here. And write the net charge out here. So we form hydronium. Hydronium is much more stable than H+. H+ is too unstable. But hydronium is a bit more of a pain to write out. And so in this class, I'm often going to write H+. But what I mean is H3O+. But I don't want to write H3O+ because it takes up more space. It's more hassle. In Chem 1B, I'll write H3O+ exclusively. In Chem 1A, I pretty much write H+ exclusively. But realize that H+ is not stable at all. And hydronium is stable. So really, this is H3O+, but if I write H3O+, then I have to balance everything. So I'll need water. They have water on the left, but I'm not going to do that. I'll just leave it like this. Okay, is this a chemical or physical? Is that chemical or physical? H+ and water going to H3O+. Chemical or physical? This is chemical. This will be an acid-base reaction here. So let's go back and look at HCl. So HCl consists of H+, and Cl minus. So we already looked at the metathesis. Did we finish the metathesis properties? Yeah. Okay. H plus likes what anion? H plus likes all the base anions stronger than water. Good. What cations does chloride like? Did we do that? Chloride actually likes only 3 cations. What are they? Silver ion, lead 2, and mercury 1. All those will cause it to precipitate out, but other than that, that's it. All right, now when we go to acid base, H plus is pretty much the same thing, except it doesn't have to be an anion. H plus reacts with all bases stronger than water. So an example here would be H plus ammonia. I'll draw out the Lewis structure for ammonia here. When we do bond polarity, we just look at delta EM. What's more electronegative, nitrogen or hydrogen? Nitrogen is more electronegative. So what that's going to do is going to do something called polarization of this bond. It's going to polarize it towards nitrogen, making nitrogen delta minus. Now look at this. This nitrogen that's delta minus, actually I forgot to do one thing, which I'll do it in a second. There's going to be an attraction. Do you see that? Electrostatic attraction here. Let's go back over here. Okay, this is not a good base, hydronium. This is a base. It can attack it like this. What about this? Going back over here, let's look at other oxygen-containing species. So another oxygen-containing species would be hydroxide. What's the formal charge on this oxygen in hydroxide? -1. When you have a non-zero formal charge, that's the actual charge on that oxygen. This oxygen literally has an extra electron. We count it. 1, 2, 3, 4, 5, 6 plus 1 gives us 7. That's 1 extra electron, which means this is its real charge. So what do you think is going to be better at attacking hydrogen ion? Water, hydroxide, or hydronium? Which of these 3 would be the best at attacking hydrogen ion? Hydroxide. And so we say hydroxide is a stronger base than water. What about this? Do you know what this is called? Well, first, what's the formal charge on oxygen? -2. This is called O2 minus, aka what's its name? Oxide. So hydroxide versus oxide, which one's a more powerful base? Oxide. Oxide is going to be a more powerful base. And so if there's a competition between these 4 species, oxide would win. Over there. All right. So there are different ways of looking at this. One is proton donor, donates to ammonia. The other is Lewis. The base attacks the acid. So this lone pair is going to attack this H plus and what's going to form from that. So when that reacts, we're going to form H, N, H, and then 2 more H's on here. Okay, what's the formal charge on nitrogen? Here. Formal charge here is 0. 1, 2, 3, 4, 5. The formal charge here is plus 1. So we write that like this, plus. This whole thing carries a positive charge, NH4 plus. Do you think we can attach another hydrogen to this? No, it's not going to work. Ammonium, it's got to stop at ammonium. What do you think is going to be a better base? Ammonia or this one? What's the formal charge on nitrogen in this species here?
-1.
-1. This is called NH2 minus. Do you know the name for NH2 minus? Amide or amide? Okay, so ammonium versus ammonia versus amide. Which one's going to be the strongest base? Amide. Sure. You see that? Amide will be the strongest base. In fact, you might have seen amide before. Where have you seen amide before? Amide is one of the strong bases. The strong bases, you memorize the strong acids, right? What are the strong bases? The strong bases are 1, the soluble hydroxides. 2, the soluble sulfides. 3, the soluble oxides. And 4, the amides. The amides are soluble. Those are the strong bases. All right, so this is what we're going to do. What we do, oxidation state, formal charge, bond polarity, delta plus to delta minus. We use the one that, for acids and bases, we use the one that tells us information. And so for acids and bases, we use formal charge and delta pluses and delta minuses. For redox, we use oxidation state. Sometimes secondarily, we'll look at oxidation state when we're looking at acid base, but it's not that common. We mainly look at those two, formal charge, delta pluses and delta minuses.
Can you say the strong base again? Because I think the potassium goes with the soluble hydroxides.
Yeah, okay. The strong bases would be the soluble hydroxides. What are the soluble hydroxides? Yeah, group 1 and ammonium hydroxide. Those are all strong bases. And so when I was talking about this, like, for example, is magnesium hydroxide soluble or insoluble? And magnesium hydroxide is milk of magnesia. People eat this stuff. That's because it's not a strong base. It's an insoluble hydroxide. So when I talked about milk of magnesia, right? Versus drain cleaner, which is a group 1 sodium. That's a strong base. But what are the other strong bases? The other strong bases are the soluble sulfides. What are the soluble sulfides? Group 1 ammonium, and group 2. So those are the soluble sulfides. What else? Are the soluble oxides. So let's say your frying pan has a little bit of rust. If your frying pan has a little bit of rust, are you going to worry too much about it? Isn't rust a strong base? No, rust is not a strong base. It's not a strong base because rust is pretty insoluble. The oxides are what we call locked in the lattice, crystal lattice. When the oxide ions are locked in the crystal lattice, it's hard for them to react. But would let's say you ran out of sodium chloride and you like the taste of sodium. Chloride has no taste, but sodium ions taste salty. And you said, okay, I want to use some sodium oxide. I'm going to sprinkle sodium oxide on your French fries. Is that a good idea? If you ran out of sodium chloride, but you need some sodium, would you sprinkle sodium oxide on your French fries? No, because that would be worse than sprinkling drain cleaner on your French fries. Is sodium hydroxide, would you use sodium hydroxide as a substitute for sodium chloride if you ran out of? No. Well, why would sodium oxide be worse? Because, oxides are more powerful than hydroxides. I just asked you that, remember? Which one's stronger? Hydroxide or oxide? And you told me hydroxide is weaker and oxide is stronger. And why would you sprinkle an even stronger base than drain cleaner on your French fries, right?
Yeah, my question is, why it doesn't seem as big to me, is with hydroxide, I get it's the -1 and oxide -2, so it's much stronger, but both ones they have, like in sodium hydroxide and sodium oxide, they both have the Na plus and balance out to make it a neutral charge. So why does it matter that it's still stronger?
Did I talk about EDTA?
Yeah.
It's because of this. When you put drain cleaner in, the reason why drain cleaner works is because it's soluble, and not only that, when you dissolve it in water, it breaks up into ions. You get the sodium ions and the hydroxide ions. And you need the hydroxide ions to attack the fats that are clogging up the sink, hair, whatever, biological stuff. Hydroxides are good at breaking certain bonds. But if you tried to pour milk of magnesia in, or if you tried to put in rust, this is not balanced, so we can balance this out. These aren't going to be as effective. And the reason they aren't going to be effective is because the ions are locked in the lattice. This is insoluble. And so it doesn't split apart. If it doesn't split apart, what happens is the hydroxide is locked in the crystal. And it being locked in the crystal, it can't break free to attack the fats or the hair or whatever that's clogging the sink. And so this is what causes this to be, even though both of these are neutral, in fact, all three of these are neutral, you aren't going to be able to use magnesium hydroxide, and you aren't going to be able to use rust, because rust should even be better. It's got oxide versus hydroxide. And so you'd expect it to be more effective at drain cleaning, but it's not. It's not because we can't use them. The ions are inaccessible. Whereas here, this ion is very accessible. Breaks very easily, so it can go on and attack. Well, this is the same thing. Sodium EDTA, the EDTA is free. It can go on and attack lead ions, control the lead population. Whereas calcium EDTA is hindered because there's calcium hanging on to the EDTA and not letting it react unless it comes across something that it likes more than calcium. Sodium EDTA, the problem with sodium EDTA is it'll attack calcium. Calcium is better than sodium, so it goes there. But if you have calcium EDTA, then it's going to need something better than calcium to attack. Otherwise, it's going to stay as is. I mean, does that answer the question for this?
Yeah, I get it now.
So this is why I say soluble. If it's insoluble, the hydroxide's locked in a lattice. It can't react. It's like jail. And the same thing with sulfides and the same thing with oxides. It's got to be soluble. Like sodium oxide will be very reactive, whereas iron 3 oxide won't be at all. All the amides are soluble. Sodium amide, etc. So these are the strong bases. There are more.
So the oxide is it group 1 ammonium or just
Group 1 and ammonium. And that's it. So H plus, going back to acid base, H plus reacts with any base stronger than water. So the strongest acid on this chart is HCl4. The weakest acid on this chart is methane. In fact, methane we don't even consider an acid. Really. The strongest base on this chart is this. This is methane. Do you know what they call this? CH3 minus? Methide. But methide isn't going to be very common. And so this is why I'm not having you memorize methide. Whereas oxides are much more, amides are much more, and sulfides are much more common. And we have, of course, hydroxides. Hydrides aren't that common, but sometimes they'll run into hydrides as well. They're strong bases. So we should memorize the common ones: hydroxide, sulfide, amide, and oxide. Okay. So this is a chart method. So I'm dealing with H plus, and I'm too lazy to write what? If I write it as H plus, I'm too lazy to write it as H3O plus, but this is our H plus here. Now, H plus is going to get in a tug of war. So if I have H3O plus and water tries to take that away, it results in a tug of war. So if I have H3O plus here, and the water comes in, I get in a tug of war for this hydrogen. Who's going to win the tug of war? This one or this one? So they're in a tug of war for this hydrogen. This water's pulling that, this water's pulling that. And The hydrogen is the positive species here. Yeah. What do you think is going to result? It's going to be a tie. So H3O plus and the base H2O is a tie. So what I need is I need a stronger base than H2O. Well, what's a stronger base than H2O? Is nitrate stronger or is trichloroacetate stronger? Okay, what was this? The strongest base is tricky because the strongest acid is top left for chloric acid. The strongest base is bottom right. And so it's upside down. The base side's upside down. And so we're going from strong on the bottom to weak on the top. And so which one's stronger? The one that's closer to, not amide, but methide. That one's stronger. So this one's stronger. So that means that H plus will react with trichloroacetate. Will H plus react with sulfate? Will it react with dihydrogen phosphate? Yes. Nitrite? Yes. Fluoride? Yes. Etc. And so most of these are anions, but not all of them. And so the difference between metathesis and this acid base is metathesis is looking for ion combinations. This, it doesn't matter if it's an ion or not. And so we have one that's not an ion, ammonia. And so this wouldn't qualify as metathesis reaction because ammonia is not an ion in that sense. So it's going to react with ammonia, yes, to form ammonia. Ammonia is a bit tricky though, but I'll talk about that more later. Okay, will H plus react with nitrate? No. Chlorate? No. And so one way of thinking about this is this. When we think about the driving force for acid-base reactions, the driving force is to go from a stronger acid to a weaker acid. That would be downhill. We're going from stronger acid, higher energy, to weaker acid, lower energy. And so this would be an uphill reaction. And this is the zigzag pattern. If we take hydronium and try to react it with nitrate, what would we form? So if we take hydronium and try to react it with nitrate, we form nitric acid and water. And so the zigzag pattern is like this. It's actually a zig and then a zag, zag. Well, maybe it's a zig, zag, zag, like that. And so this would be uphill. So we would be going from a weaker acid to a stronger acid. That's uphill. That's not favorable. And then we would be going from a weaker base, nitrate, to a stronger base. That's uphill also, but this is the inverted world of the bases. The inverted world of the bases, uphill's going down. Okay, whereas here, will H plus react with sulfate? Yes, because this would be downhill. If H3O plus reacts with sulfate, what do we form? Well, this is going to go zig and then zag here. It's going to form HSO4 minus. Well, HSO4 minus is a weaker acid. So we're going from a stronger acid to weaker acid. And the other zags here, we're going to go from hydronium to water. Water is a weaker base. So we're going from a stronger base, sulfate, to a weaker base, water. Do you guys see that? The zigzag method of the chart. Okay. Now, there's a couple of complications to using the chart. Do you know what the strongest acid that can exist stably in water? What I mean is, can H plus exist stably in water? No, it's too strong. It's too reactive. It's going to attack water right away to form hydronium. So what is the strongest acid that can exist stably in water? The strongest acid that can exist stably in water is hydronium. Hydronium is the strongest. And so the complication in this chart is any acid stronger than hydronium doesn't exist in water. It's like protons. H plus doesn't exist in water. It's going to react to form hydronium. The same thing here. When HNO3 reacts with water, now water is very unusual because water can either act as an acid or a base. It's what we call amphoteric. So in this case, if water acts as the base, if hydronium reacts with water, what forms? Hydronium. If HClO3 reacts with water, what forms? In fact, all of these, HClO4 reacts with water, what do we form? All of those form the weaker acid hydronium. So the strongest acid that can exist in water is hydronium. All these acids do not exist as is in water. They all split apart or form hydronium. That forming hydronium is called hydrolysis. And so this is called the leveling effect. Of strong acids. It's not really discussed in our book. So we'll just go to Wikipedia. This is the Wikipedia for the leveling effect. And so let's just take a look at this starting here. Any acid that is stronger than hydronium reacts with water to produce hydronium. So let's pick the strongest acid, HCl4. React that with water, it's going to form hydronium and ClO4 minus. Let's pick a little weaker acid, HCl. HCl reacts with water to form hydronium and Cl minus. Let's pick the weakest of the strong acids. The weakest of the strong acids is HNO3. We're going to react with water to form hydronium plus nitrate. I'm going to leave off aqueous, but I'll write in liquid, solid, gas. In this case, liquid. So let's keep reading here. Therefore, no acid stronger than hydronium exists in water. For example, aqueous perchloric, HClO4, aqueous hydrochloric, HCl, and aqueous nitric acid are all completely ionized and are all equally strong acids. So in other words, it is true HClO4 is a stronger acid. What it means to be a stronger acid is it loses its hydrogen easier than HNO3. But all of these lose it very easily to water. Water has no problem plucking the hydrogen off any of these. And so what results is the same amount of hydronium for all three. And so if I have 1 molar solutions of each of these, all of them are going to produce 1 molar solutions of hydronium. You can't tell the difference. Since we get the same amount of hydronium for all three of these, then that's the leveling effect. Even though HClO4 is the easiest to pluck it off, water has no problem plucking it off HNO3. And so all are the same strength in water. So water has no problem plucking the H plus off any of those acids. However, it's going to have a problem plugging it off here. So for example, if I went from trichloroacetic acid and water, what would I form? So if I take trichloroacetic acid and water, I'm going to form hydronium. And so I'm going from a weaker acid to a stronger acid. Is that favorable? No. And so that's uphill. And so if I go trichloroacetic acid plus water, I would form hydronium, but that's uphill. Not favorable. So I'm not going to form much hydronium. Now, if I go phosphoric acid and water, that's even farther uphill. Even less favorable. If I go acetic acid here and water, that's even farther uphill and becoming less and less favorable. So if the hill's not too steep, then I can form a little bit of hydronium. But the steeper the hill is, the less hydronium I'm going to form because the fewer molecules that can collide to yield a population up here. And so the weak acids partially ionize. The stronger weak acids ionize more. The weaker weak acids ionize less. The acidity is going to be dictated by how much hydronium you produce. Now, all the strong acids produce the same amount of hydronium, except for H2SO4, which produces a little bit more. But the weak acids produce varying amounts of hydronium depending on how weak they are. So that's a leveling effect. And so it becomes a little bit tricky when you're dealing with a scenario like this. Let's take HCl as an example. For HCl, you'd say if HCl got in a tug of war with chloride, who'd win? Well, chloride versus chloride is going to be a tie. So we need a base that's stronger. Which is stronger, bromide or HSO4 minus? HSO4 minus. So let's pick HCl and nitrate. If HCl and nitrate react, what forms? Nitric acid. So we're going from hydrochloric to nitric. That's downhill, right? And therefore, we expect this to work. Here's a zig, zag. That's downhill. But we get no reaction. The reason we get no reaction is because all these are equivalent in water. And so there's no reaction here because if we go from HCl to HNO3, it isn't getting any weaker or any stronger because they're the same. Does that make sense? That's the leveling effect. Whereas here it makes a difference. If we go to HCl and react with sulfate, yes, we're going to get a driving force for that. That's downhill. Versus, let's say, HNO3 versus sulfate. That's also downhill, but it's going to be downhill less. You know what the strongest base that can exist in water is? The strongest base that can exist in water stably is hydroxide. So the strongest acid is hydronium, the strongest base is hydroxide. So let me say, you know what? I want to make a 6 molar solution of oxide. Is that going to be possible? It turns out it's not going to be possible because oxide is too strong to exist in water. What happens is the oxide will attack water. When oxide attacks water, what does it form? Hydroxide. Well, what about amide? When amide, I try to make a solution of amide, the amide is too strong. Amide attacks water to form hydroxide. Sulfite attacks water to form. Methide attacks water to form. And so what that means is the strongest base that can exist in water is hydroxide. We can have weaker bases, like when hydroxide attacks monohydrogen phosphate, we form phosphate. Phosphate's a weaker base. But we can't have a stronger base than hydroxide in water. And so that's called the leveling effect of strong bases. so let's just say and strong bases. In other words, all the strong bases have the same strength in water, except for one. All strong bases have the same strength in water. Let me put a little asterisk because it is a little bit more complicated. The asterisk there involves like oxide. When oxide attacks water, what forms? Hydroxide, and then the oxide is converted to hydroxide, so we get double the amount of hydroxide. And so oxide yields more hydroxide than the other. And then there's another reason for the asterisk. And that is, they're not exactly equal, but they're close enough. All right, so if we have H plus, then we can figure out what base is. But we're going to look at chloride next. Chloride is a base. So chloride being a base, we want it to attack like HCl. HCl versus chloride, which chloride wins? The proton. It's a tie. We need an acid that's stronger than HCl. What acid is stronger than HCl? HBr. HBr is stronger than HCl. And so if chloride reacts with HBr, we're going to form bromide and HCl. So we're going from HBr to HCl. But there's a problem. The problem is the leveling effect. The leveling effect is going to tell me, is HCl really a weaker acid than HBr? No. They're the same strength in water. Well, let's go with something even stronger, HI. If chloride reacts with HI is stronger, isn't it? Then we should certainly have a drop in acid strength, which means driving force, which means reaction. But is HI stronger than HCl? No. What about HClO4? So chloride reacts with HClO4, we're going to form HCl. So perchloric. Then there's got to be reaction there, right? But now we're at the top. Is there any acid stronger than HClO4 on this chart? You see any acids from? No, I'm at the top. So what does that mean? Yes, chloride's a base, but what acid will react with this base? None. Because all these are too strong to exist in water. And therefore all these get converted to hydronium. Hydronium is the strongest acid that can exist in water. So if we take chloride and react it with hydronium, is that favorable? If we take chloride and react it with hydronium, we're going to form HCl. And so are we going from stronger to weaker? No, we're going from weaker to stronger. Is that favorable? No, that's uphill. And so we don't expect any reaction there. And since all those form hydronium, then we get no reaction. And if there's no reaction, even though, yes, it's a base, this is what we call conjugate base, so this is a conjugate pair. This is the acid, this is the base, and they're conjugates of each other. This is a base, I have to put base asterisk. And the footnote that I have to add here is this. This is too weak to be basic in water. In other words, we call it neutral. Chloride's neutral. And the conjugate relationship, there's different ways people explain it. And one way is the conjugate relationship. A strong acid, the H plus has to break off easily. Strong acids are strong electrolytes. If the H plus breaks off easily, that means chloride had barely any hold on it. Chloride wasn't holding on to the hydrogen. If chloride held on to the hydrogen, then it wouldn't break off so easily. And therefore, if we have a strong acid, its conjugate is going to be extremely weak. And if we have a strong acid, its conjugate is going to be so weak of a base, we don't even consider it a base. And so let me ask you this. We use table salt, and so most people have table salt at home. Let's say you ran out of antacid. Antacid, you want to neutralize the acid in your stomach. You ran out of antacid, could you use sodium chloride as an alternative? Sodium chloride as an alternative. In other words, will sodium chloride, table salt, neutralize your stomach acid? No, because sodium ions, they aren't going to do anything. The chloride is definitely not going to do anything. Does that make sense? And so sodium chloride you can use. So that's another way of thinking about this. So chloride, yes, acid-base properties, essentially neutral. Not an acid, not a base. Although it is a conjugate base here. It's just too weak. All right. So the acid base, we use a chart. The chart, this chart is a Bronsted acid base chart. The only problem with Bronsted is not all acids are Bronsted acids. We have other acids that don't fit this. The other acids that don't fit it are Lewis. The Lewis chart is complicated. We'll talk a little bit more about Lewis later. Okay, the next thing we're going to look at is redox. What types of redox reactions have we encountered so far? We've encountered element plus element combination slash in the reverse would be decomposition. So an element like iron reacting with oxygen to form rust, iron 3 oxide. Need 2 irons, 3 oxygens, 3 halves of oxygen. The forward is combination, the reverse is decomposition. This is a redox reaction because iron, what's the oxidation state in an element, in elemental form? 0. So the oxidation state of iron is 0. What's the oxidation state on oxygen? 0. Elements in elemental form have oxidation states of 0. Okay, what are the oxidation states in iron 3 oxide? Yeah, plus 3. Oxidation state, I'm going to be consistent. Oxidation state go in parentheses. Formal charges are circled. Plus 3 minus 2. So iron went from 0 to plus 3. What happens? Well, it's got to lose electrons. Oxygen went from 0 to minus 2. It must gain electrons. Redox reactions are electron transfer. So electrons were transferred from the iron to the oxygen going forward. Going reverse Electrons are transferred from the oxygen back to the iron. Then we have single replacement reactions. You recall single replacement reactions? They follow a form. A plus Bx yields Ax plus B. In order to do single replacement reactions, we need the activity series. Here are the activity series. Looks something like this. At the top of the activity series is lithium, and then it goes down. So let's do an example of a single replacement. Zinc solid plus nickel 2 chloride. What does this form? It's going to form zinc chloride. What's the charge on zinc? Zinc only has one charge in cation form. What is it? Plus 2. And so this will be ZnCl2. Zinc metal, what's the oxidation state of zinc on zinc metal? Nickel plus 2, in this case chloride, minus 1. Zinc plus 2, chloride minus 1. So we're going to form zinc chloride, ZnCl2, I'll need 2 chlorides to balance it, plus nickel metal. Nickel metal is going to be 0, so it's just going to be solid metal. And then we consult the activity series and see. In the activity series, we want to go from more active to less active. And so here, zinc, the most active is lithium. So zinc is more active than nickel. We're going downhill here. And so what we say is that zinc is the more active. More active means more reactive, less stable, higher energy. Nickel is less active. Less active is more stable, lower energy. And this will be the driving force. So we expect reaction here using the activity series. The advantage of single replacement is it's easy and quick. You know what the disadvantage is? That it's sometimes wrong. There are exceptions. You know, it's a simple pattern. We like to remember things as simple patterns. I mean, that's what scientists do. They look for patterns, but sometimes the patterns don't hold up. Sometimes there are a lot of exceptions to the pattern. You know, these rules of reaction don't necessarily work so well. So let me tell you some exceptions. One example would be something like this. We'll do sodium solid, sodium metal plus potassium chloride, aqueous. What forms here? Yeah, sodium chloride and potassium metal. And then we go to the activity series and we go, okay, here's sodium, here's potassium. So we're going from sodium to potassium. Is that uphill or downhill? That's uphill. That's not favorable. So what that means is we're going from less active sodium to more active potassium. That's uphill. The downhill directions are reversed. And therefore what we say is NR. NR means what? No reaction. But this turns out to be wrong. This is correct. There is no reaction producing these as a product. Turns out to be wrong. So, why is it wrong? And the reason it's wrong is because we're locked into looking at a simple pattern. And so we're kind of blinded, you know. We are just looking at this pattern, and that's it. And so what we can do is there's another method of solving redox, and that's called the chart method. You can try this as an alternative to single replacement, or you can use the chart method and single replacement. If you know the single replacement should work, then you can use single replacement because it's quick and easy. With the chart method, we don't restrict ourselves to a simple pattern. In the chart method, we look at what we have. And so in the chart method, the first thing we do is inventory everything. And so what's present in this mixture? We have sodium metal. We have KCl aqueous. KCl aqueous is soluble. All group 1 salts are soluble. Is it a strong electrolyte, weak electrolyte, or non-electrolyte? Strong. And so KCl aqueous is going to consist of potassium ions and chlorine ions. But there's something missing. Do you know what's missing? Water. Water is missing. Sometimes water is important. In fact, you know, water is probably the #1 ingredient, wouldn't you say, in this reaction mixture? Water is the #1 ingredient in this reaction mixture. And do you know what happens when sodium comes into contact with water?
A small piece of soap. Pounds of highly dangerous minerals for destruction in Lake Lenore, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises to a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Asset Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
So when we're locked into this A plus BX pattern, there should have been one more thing, right? Plus water, the solvent. And so when we're locked into this pattern, sometimes we don't see the other stuff. And sometimes the other stuff is important. And so therefore we have an alternate method. And the alternate method is a chart method where we consider everything. And when we consider everything, we consult the redox chart. Now the redox chart is going to be very similar to the acid-base chart in organization. It looks a little bit more complicated here, because in redox reactions, we're transferring electrons, so the electrons are shown here. Now, certain things take electrons, so all these species on the left here are taking electrons. There are 2 electrons, 2 electrons, 2 electrons, 5 electrons, 6 electrons here. So these species are taking electrons. The species on the right side, we go backwards. The species on the right side lose electrons going backwards. Here. Actually, it doesn't go backwards, it goes forwards. It's just, we don't want to write, you know. So for example, we don't want to write 2 separate tables, one table for the acid, one table for the base. The same thing here. We call things that take electrons oxidizers. So we put all the oxidizers on the left. Do you know what the strongest oxidizer is? Fluorine. Fluorine's the strongest oxidizer. That means it really wants to take electrons. What do you think? Once it grabs electrons, does it let go of them easily? No. Once fluorine grabs electrons to make fluoride, fluoride is stable. It's very unreactive. And this is called the conjugate relationship. So if we have a very strong oxidizer, its conjugate reducer, fluoride, is very weak. It doesn't want to lose electrons. The strongest oxidizer on this chart is fluorine. Do you know what the weakest oxidizer on this chart is? The weakest oxidizer on the chart is lithium ion. Lithium ion is very weak. It doesn't really have much strength to grab an electron. And once it does, it doesn't hold on to them tightly. And so its conjugate isn't so weak. Its conjugate is strong. And so lithium is the strongest reducer on the chart, meaning it loses the electrons the easiest. And so lithium is a powerful, well, a strong reducer, meaning it gives up the electron to form lithium ion. So lithium ion is stable. Lithium metal is unstable. Versus at the top of the chart, fluorine is unstable, fluorine is stable in terms of redox. And so we have one chart that shows this oxidizers on the left and the reducers on the right. Now take a look at the reducers here. It goes lithium, potassium, calcium. Have you seen that before? You might have seen that before. Because look at lithium, potassium, calcium. We've seen it before, except we called it the activity series. So what we have here is we have an upside down activity series. At the top of the activity series is lithium. And so the activity series are just the strength of the reducing agent. And so the last example we did was, what was it? Nickel and zinc. So here's zinc, and then unfortunately nickel's not on this chart, but nickel would be up there. And so we could see zinc is more active than nickel. Now we only have to use one side of the chart. And so oftentimes in metathesis, we say stronger acid to weaker acid. But if you're dealing with an acid, then you also have a base. But we don't have to do both. We could just say we're going to go from stronger reducer, that is the more active, to weaker reducer, less active. So we can use the activity series. And the reason we can do that is because of the conjugate relationship. Because of the conjugate relationship, if we're going from more active reducer to less active reducer, then that must mean the same thing in terms of oxidizers. In terms of oxidizers, we must be going from a stronger oxidizer to a weaker oxidizer. It's the zigzag part of this. And so all we're going to do is we're going to identify each of these. So sodium, oxidizer or reducer? Sodium is it on the left side or the right side? It's on the right side. The right side are the reducers. And so sodium is a reducer. But I know spelling out reducer is too long. I just abbreviate it RA. RA stands for reducing agent. Okay. We don't have sodium ion, we have sodium metal. We have potassium ion. Potassium ion is on the left side or the right side? Left, and therefore it's a oxidizer. And so below potassium, I'm going to write OA. Chloride. We'll look for chloride. Let's try the right side. Right side meaning it's a RA. Now I'm going to quit saying left side and right side. I should say the fluorine side or the lithium side, because sometimes the charts are flipped upside down. Water. Fluorine side or lithium side? Well, I see water here. And therefore, this is on the lithium side or fluorine side? Lithium. That means water is a reducer. But I see water here and I see water here. Look at, do you see that? There are two waters here, there are two waters here. There are waters here and here and here, but these waters also have this other stuff. But when I have water here and water here, which of these two waters should I use? Should I use the top water here or the bottom water here? The bottom, why?
Well, the top one is, on the left side is hydrogen peroxide, and then on the bottom is just oxygen. Hydrogen.
Okay. Yeah, you might think, well, water's water, so aren't these the same? No, they aren't the same. They are the same, yes. They're different because of the product they form. And so this water goes to oxygen. This water goes to hydrogen peroxide. So what's more stable, oxygen or hydrogen peroxide, would you say? Oxygen. And so this is a more stable product, therefore we're going to pick it. The other way of determining this is the stronger. You always pick the stronger. So which one's stronger, this water or this water? The second water. This water is stronger, and therefore we're going to pick that one. It is the most reactive species are going to react. And so water occurs on the lithium side. But did you know water also occurs on the fluorine side? It occurs on both sides. It's just like the acid base. Water can act either as an acid or base. But when I look at water here, do you see it's on the fluorine side? Wait a minute, didn't I say lithium ion was the weakest oxidizer? Shouldn't water be the weakest oxidizer? It's at the bottom of the chart. And the answer is no. It's unfortunately we had to split up the chart. This is two different charts here. And so when we look at water, water actually is not at the bottom. Zoom out. So where we're going to position water depends on the numbers on the right here. So if you look at this number, these numbers we use in Chem 1B, but not in Chem 1A. We're going to use it for this though. It's minus 0.828. Minus 0.828 places it in here. If you place it in here, then I wrote 3 dots here. These 3 dots here mean to insert water. And so water belongs here. Water is weaker than zinc ion, but stronger than aluminum ion. So water fits right there. And so water is both a reducing agent and an oxidizing agent. It's also both an acid and a base. Both an acid and base we call an amphoteric. But here we have this. And so we identify each of the species. All right, we'll take a break here and then we'll finish this after a break. All right, once you ID these, then you want to pick the 2 strongest. The strongest reducer and the strongest oxidizer. And so we have 3 reducers, sodium, chloride, and water. And so we'll take a look at the chart here. Lithium's the strongest reducer, and the first one we hit is sodium. Here. The next one we hit is water here, and then chloride. And so sodium is the strongest reducer. And then let's look for the strongest oxidizer. For the strongest oxidizer, we start at fluorine and then work our way down. And it's just going to be between water and potassium ions. So the first one we hit is water, which is here between zinc ion and aluminum ion, and then potassium down here. So the strongest oxidizer will be water. It doesn't mean a reaction is going to happen, but the most likely reaction will be between the 2 strongest species, sodium and water. And so what would that reaction be? So for water, we could just write it as is. Water is reactive. And we write that, that's called a half reaction. So we'll take 2 waters plus 2 electrons, produces hydrogen gas plus 2 hydroxides. Now for sodium, we don't have it because in this case, sodium is a product. So what we're going to do is we're going to just reverse this equation to make sodium a reactant. So reversing that second half reaction, we get sodium solid goes to sodium plus an electron. And so I have the 2 reactants here, water and sodium. Okay, the next step is I'm going to add up the 2 half reactions. But when I add them up, I have to make sure that the electrons that are transferred balance. Redox reactions are electron transfer reactions, so we're going to transfer electrons from the sodium to the water. But in this case, sodium only produces 1 electron, water needs 2 electrons. And so how can I fix that? Yeah, I'll double the sodium. So I'll just take this second one and just multiply it by 2. And then what I'm going to do is I'm going to add up all the reactants and all the products. And so I'll have 2 waters plus 2 electrons plus 2 sodium solids. And then I'll add up or combine all the products. And the products will be H2 plus 2 hydroxides plus 2 sodium ions plus 2 electrons. Okay, then what we do is I'll simplify this. Simplifying this, the 2 electrons need to cancel. Redox, we have to have transfer. So we can't have leftover or missing electrons. And then what else cancels? It looks like it. And so overall, the reaction is going to be 2 waters plus 2 sodium solids. This is going to produce hydrogen gas plus 2 hydroxides plus 2 sodium ions. And so this is the reaction we end up with here. Next, we got to look for driving force. The driving force is we want this to go downhill, and so we have to assign these. So, for example, the water is the oxidizer. Oxidizers take electrons. So, water is our oxidizing agent, OA. Sodium is our reducer. Sodium is losing electrons. That's our reducing agent. So what we want to do is we want to go from stronger to weaker. But how do I assign these? What's the oxidizer? What's the reducer for the products? For the products, what I'm going to do is I'm going to take advantage of the conjugate relationship. And so water, as we call, is the oxidizer. So the oxidizer, the conjugate of that will be the reducer here. So for the oxidizer water, its conjugate reducer will be hydrogen and hydroxide. So hydrogen and hydroxide, this will be our reducer. And sodium is our reducer, and its conjugate oxidizer will be sodium ion. And so this will be our oxidizer here. So we want to go downhill. So I'm going to compare sodium and hydrogen and hydroxide. So when I look at my chart, sodium's here, and hydrogen and hydroxide are here between zinc and aluminum, because I got to insert the water there. And so we're going from stronger, sodium, which is closer to lithium, to weaker. We only have to look at one, so this is activity series here. Sodium's more active, hydrogen hydroxide is less active. But we only need one because of the conjugate relationship, but if we want, we could take a look at the oxidizer too. So when we look at the oxidizer, water's here versus sodium ion, which is here. So we're going from stronger oxidizer, it's closer to fluorine, to weaker oxidizer. And so the oxidizers have to follow the same pattern, stronger to weaker. So it's always going to be strong, strong to weak, weak, or weak, weak to strong, strong. It's never going to go strong, weak, No. And so we have driving force here. And so the reaction wasn't between water, the reaction wasn't between sodium and potassium chloride. Nothing happened with potassium chloride. The reaction was between sodium and water. And the explosions that you saw in the video were a result of hydrogen exploding with oxygen and air. You know, this reaction is quite exothermic, so it generates heat. That's what you see. Let me give you two more examples of where it fails. So one mode of failure is it's too narrow. You know, we weren't looking at everything being the water, which is the solvent. The other reason it fails is because it assigns roles to each species, and sometimes they aren't the best species for that particular role. So when we look at A plus BX, A is assigned, let's say you're the director of a play, you assign A as the reducing agent. So A, you're supposed to lose electrons. Do you know what B is assigned? B is the oxidizing agent. X is, well, if we do this, did I do the, let's see. Seems to work. X is what we call the spectator. So if we go back to the earlier reaction, zinc plus nickel 2 chloride yields zinc chloride plus nickel. Seems to work here. Zinc goes from an oxidation state of 0. Elements in elemental form is 0. And the charge on zinc and zinc chloride is plus 2. So what happened? Well, zinc lost electrons. Reducers lose electrons. So this was correctly assigned. What's happening with nickel? Nickel's going from +2 to 0. So in order to go from +2 to 0, it must gain electrons. Well, species that gain electrons are the oxidizer. What happened to chloride? Chloride went from -1 to -1. So nothing happened to chloride, therefore chloride is the spectator. The problem with this is, what if, seemed to work out here, but what if it didn't quite work out? So let's do this. Let's take a look at this example here, copper plus HNO3. In this particular one, the role of copper is the reducer. The role of H plus is the oxidizer. So that should be H plus. And the role of nitrate is spectator. Well, copper is a pretty decent reducer. It's not the best. I would just say it's moderate. It's here. We look at the whole chart, it's kind of in the middle. It's an okay reducer. Here's lithium. It's a moderate reducer. I don't think there's anything wrong with that. Copper is going to be a much better reducer than water, so we don't have to worry about water. And then the oxidizer is going to be H plus, which is here. Would you say H plus is a strong oxidizer, moderate oxidizer, or weak oxidizer? Well, here's lithium ion, here's H plus, and at the top is fluorine. So it looks a long way off fluorine, but you know, this is nonlinear. And so there's a tremendous, from H plus down to lithium ion, there's a tremendous decrease in oxidizing strength. And so we call H plus a moderate oxidizer. So H plus is a moderate oxidizer. You know what's a much better oxidizer than H plus? Well, a much better oxidizer would be something like nitrate. You see that? Nitrate is a much better oxidizer than H plus. But what role was it nitrate assigned? Spectator. Now, if you're the director of this reaction, you got to tell nitrate not to react, because nitrate is supposed to be a spectator, and so nitrate must not react. So how can you tell nitrate not to react? I mean, if you have a beaker, what would you say to the beaker to get nitrate not to react? I mean, is there something you could tell nitrate don't react? No? What do you think is going to happen? It's going to react. If it reacts, then all the roles you just assigned are incorrect. And so, single replacement failed. A plus Bx yields, okay, we're going to form what? Copper. Now, copper has two common charges. What are they? Copper plus 1 plus 2. What's more common, +1 copper or +2 copper? It turns out +2 copper is more common. If you look at copper here, the only ion it forms is copper 2. And so if we form copper 2, we'll need 2 nitrates to balance it. And what else? And hydrogen. To balance this, I'll need 2 nitric acids. Okay, then I compare, this is activities, you know. So copper, we look at the activity versus hydrogen. So which one's more active, hydrogen or copper? Lithium's at the top, so hydrogen is more active. And so we're going from a less active to a more active. And so downhill is backwards this way. And so what we say is the driving force is reversed here, downhill is backwards, and therefore there's no reaction in R. But this is wrong. It's wrong because we misassigned it. Nitrate's not a spectator. Nitrate's more powerful than H+. It's wrong. We have to must use the chart method. So if we do this using the chart method, it's okay. Let's do another example of an A plus BX pattern. Let's take chlorine plus potassium bromide. What were the roles? So A is what? Reducing agent. Is chlorine a good reducing agent? If you look at the top, oxidizes fluorine, chlorine, bromine, iodine. Do you see all of those are good oxidizers? Do you see chlorine anywhere on the reducer side? No. Chlorine's not a reducer. Chlorine's an oxidizer. If chlorine's an oxidizer, our pattern fails. And so single replacement fails. We have to use the alternate pattern. The alternate pattern is the X2 plus AY pattern. X2 plus AY yields AX plus Y2. Or chart method. So you have to know, this is an example of what we call an oxidizing acid. HCl is an example of mineral acid. When we think about HCl, chloride's pretty unreactive. And it's certainly not an oxidizer. Mineral acids, only H plus is the oxidizer. So mineral acids fit this role for BX. But oxidizing acids don't fit this role because all oxidizing acids have an X that's a more powerful oxidizer. So nitric acid is called an oxidizing acid because nitrate is more powerful than H plus. Here's H plus. Sulfuric acid is too. Sulfuric acid consists of sulfate and H plus, H2SO4. H2SO4 is an oxidizing acid because sulfate is not a spectator. Sulfate is more reactive. Do you see that? What else? Nitric acid, iodic acid, etc. And so we need to know this. If you want to use single replacement, you have to be careful. You have to be careful that you don't miss species that are left out water. You don't assign X as a spectator when it's not a spectator, oxidizing acids or nitrates, all that kind of stuff. Or, for halogens, you use an alternate pattern or the chart. The chart method works for all these, so you can just use the chart method, which we just went through. So for redox, we have the combination, decomposition. For elements, compounds. We have single replacement. We have the chart method. Chart method you could use in lieu of the single replacement. And the chart method is a bit more powerful than single replacement. we have combustion reactions, and we have skeleton reactions. Skeleton reactions are a little bit different. Skeleton reactions, you're given the major products, and so we don't have to predict them. We just have to balance it. Let's say I was combusting my methane. There's easier ways of doing this balancing. And the major product was carbon monoxide gas. And so what I want to do is I want to just balance this reaction. And so we're given the major product, in this case, CO. When I balance it, the first step is to split it into half reactions. So methane goes to CO, and oxygen goes to blank, question mark. So the first thing is to split it into half. Here, I don't really care. Oxygen and hydrogen always balance. And so I could leave it blank with any kind of oxygen-hydrogen containing species. Here, the carbon all ends up in carbon monoxide. And so in skeleton redox, we balance all elements other than oxygen and hydrogen. And so over here on the left, I have one carbon. On the right, I have one carbon. And so it's already balanced. If it wasn't balanced, I wouldn't add carbon, which would be soot. I just change the coefficients. Okay, then I balance the oxygens. Over here on the left, I have no oxygens. On the right, I have one oxygen. But I balance it in a strange way. When I balance the oxygens, I add water. So I'm going to add one water to the left, and that's going to balance the oxygens. After I balance the oxygens, then I balance the hydrogens. So I have 4 from methane plus 2 from water, which gives me 6 hydrogens on the left. And then I just have carbon monoxide on the right, so there are no hydrogens on the right. And so I balance it by adding H+. So I'll add 6H+ on the right. Okay, then I balance the total charge. Net charge on the left, methane's neutral, water's neutral, so it's 0. Carbon monoxide is neutral, but H+ is +1 times 6 is +6. The way I balance the charge is by adding negative charges, electrons. And so I do +6 minus 6 from the electrons. That gives me 0. And so overall, the half reaction here is going to be CH4 plus H2O. Liquid yields CO gas plus 6H plus 6 electrons. And so this is called a half reaction. The other half reaction here is oxygen. Oxygen goes somewhere. And so I just start to balance it. I have 2 oxygens on the left and 0 oxygens on the right. And so what do I add? 2 waters. Okay, then I balance the hydrogens. I have no hydrogens on the left and 4 hydrogens on the right. So I'm going to add 4H+. And then I balance out the charge. I have 0 plus 4 on the left and then 0 on the right. And so I'm going to add 4 electrons. And so the other half reaction, I'll just add everything up. O2 plus 4H plus 4 electrons yields 2H2O. Redox reactions are electron transfer. And so what I got to do is I'm going to make sure the electrons balance. So it looks like 12 is a common factor between these. So I'm going to multiply the top one by 2 and the bottom one by 3. And then combine them. So I'm going to add up all the reactants. 2 methane plus 2 water to the top. And the bottom is going to have 3 O2 plus 12H plus 12 electrons. So that's all the reactants. And then let's combine all the products. 2 carbon monoxides plus 12H plus 12 electrons plus 3 times 2 is 6H2O. And then I'm going to simplify this here. Looks like the 12H pluses cancel, the 12 electrons cancel. And then 2 waters will cancel 2 of these, leaving me with 4. And so I'm going to get 2 methane plus 3 O2 yields 2 carbon monoxides plus 4 H2O. And then I double check this. When I double check this, I just look, are the atoms balanced? So 2 carbons, 8 hydrogens, 6 oxygens, 2 plus 4, 6 oxygens. Atoms are balanced. Then I check for charge balance. 0, 0, 0, 0, 0, 0. Charge is balanced. And so this is balanced. Now, this is a skeleton redox, so we're given the major product. If we're given the major product, then we know the reaction occurred. And so there's got to be driving force. So when I look at the methane and water, do the methane and water gain electrons or lose electrons? Methane plus water lost electrons. Do you see that? If you lose electrons, this is called Ra. So the reducing agent is methane and water. Over here, the oxygen and H plus gained electrons. So the oxygen and H plus, this is our OA. So our Ra is methane and water. There's no water here, so it's just going to be methane. This is our Ra. Our OA here is going to be oxygen. Okay, then I'm going to use the conjugate relationship to figure out the products. So if this is my reducing agent, then this must be the conjugate oxidizing agent here. So the oxidizing agent is CO and H plus. There's no H plus, so it's just going to be CO. That's my oxidizing agent. And the reducing agent is going to be just H2O. H2O going backwards gives up electrons. So this is my reducing agent here. Now we know this reaction happens, so we got to be going from stronger to weaker. And so what this means is that oxygen, O2, is a stronger oxidizer than carbon monoxide, and methane is a stronger reducer than water. So we don't have to consult the chart for that. That's what happens in skeleton redox. So we do this because these charts aren't comprehensive. Do you know where a more comprehensive chart is located? This is taken out of the chapter. The more comprehensive chart is located in Appendix B. But even with the more comprehensive chart, sometimes there just aren't things there. Or sometimes the reactions don't happen as you plan. Because normally when we combust methane, we don't form carbon monoxide. Normally when we combust methane, we form carbon dioxide. And so in this case, we got a different product. And that just depends on the conditions that you do the reaction under. Did I tell you about my camping trip to Joshua Tree? Probably in Camp 4. I told you. I went to the dollar store. Did I tell you that? Yeah. Well, for those of you who haven't heard the story, I went camping in Joshua Tree. At the dollar store, they had a $1 bottle of Santa Barbara wine. So I bought it. When I took it back to the campground, you know what it tasted like? It didn't taste like wine. It tasted like vinegar. It tasted like vinegar, which has the formula CH3COOH. I figured what happened was some air must have leaked into the bottle through the cork and unfortunately oxidized my ethanol to vinegar, acetic acid. Normally, when you oxidize ethanol, do you know what you form? So, well, instead of oxidize, let's say burn. When you burn ethanol, what do you form? So if you were to burn ethanol in a fire, would you form vinegar? No. When you burn ethanol in a fire, what do you get? CO2. That's what I was hoping. I was hoping to metabolize, i.e. burn the ethanol in my body and then exhale CO2. Because your body is going to take maximum advantage of it. You're going to inhale oxygen. Here we have the fuel, and we want to maximize the metabolism of our ethanol and exhale CO2. If we exhale CO2, then we know we've extracted all the energy there is, because we can't go any further than CO2. And so what this is called is, this is partial oxidation. It's like the previous problem. You know, really, when you combust methane, you should go all the way to CO2, but that was only partial reaction. In this case, we have partial oxidation, because if I metabolize the ethanol, I should metabolize it all the way to CO2 and extract every little bit of energy there is to extract out of the ethanol. But I didn't, or at least the bottle of wine didn't. And so what happened here? So this is an example of a skeleton redox. The skeleton redox is the ethanol got converted to acetic acid, and the oxygen got converted to what? Now, oxygen, we don't have many choices. When oxygen is not balanced, what does it form? Well, to balance out the oxygens, you add water. And so here, the oxygen's got to go to water. Well, if oxygens go to water, then this is the balanced half reaction here. Does this one look familiar? And so this is from the chart. So off the chart, we have O2 plus 4H plus 4 electrons yields 2H2O. This is from the chart. And so this is going to be a hybrid skeleton redox. It's going to be hybrid because it's going to be skeleton plus chart method. Okay, do I see ethanol on here? No, there's no ethanol on here, so I'm going to have to figure this one out. And so the first thing is balance all elements other than oxygen and hydrogen. So I have 2 carbons here on the left. I have 2 carbons on the right, so it's balanced. Then I balance the oxygen. So I have 1 oxygen on the left, 2 oxygens on the right. And so what do I add? H2O. Then I balance out the hydrogens. So let's total them up. 3 plus 2 is 5, plus 1 is 6, plus 2 is 7. Oh, 8. 8 oxygens. 8 oxygens on the left, and then I have 2 oxygens on the right. Oh, no. Hydrogens, sorry. 8 hydrogens on the left, 4 hydrogens on the right. And so I'm going to add 4H plus to the right.
Don't we just have 6 hydrogens on board?
Oh, yeah, right, 6. Well, 3, 4, 5, 6, 7, 8. 8. Then I got to balance the charge. Ethanol is neutral, water is neutral, so that's 0. Acetic acid is neutral, H plus is plus, so it's plus 4. And then I'm going to add what? To which side? Right side. And so the balanced half reaction here is going to be ethanol plus water yields acetic acid plus 4H plus 4 electrons. And then I combine the 2 half reactions. But combining them, it's nice because the electrons are balanced. So electron transfer, the electrons have to be balanced. So they're already balanced, so I'm just going to combine them as is. So I'm going to CH3CH2OH, ethanol, plus water, plus O2, plus 4H plus 4 electrons. Okay, those are all my reactants. And then I go to the products, which would be acetic acid, CH3COOH, plus 4H plus 4 electrons, plus 2 waters. All right, and then let's simplify things. The 4 electrons cancel. The 4H pluses cancel. One of the waters cancels here. And so what I end up with is ethanol plus O2 yields acetic acid plus H2O. And I check, are the atoms still balanced? 2 carbons, 3, 5, 6 hydrogens, 4 plus 2, 6 hydrogens, 1, 2, 3 oxygens, 1, 2, 3 oxygens. So the atoms are balanced. Then I look for the charge, 0 plus 0, 0, 0 plus 0, 0. Charges are balanced. So this is it. And the final thing is the driving force. I already know this reaction occurred because I could taste the vinegar. The reaction must have occurred. But I'm just going to assign them here. And when we assign them, we go back to the half reactions here. Looking at this half reaction, is this the oxidizer or the reducer? Ethanol, was it the oxidizer or the reducer? Ethanol is the reducer. Ethanol in water is the reducer because it produced electrons as a product. And so this is my reducer. And therefore, this must be the conjugate oxidizer. So acetic acid and H plus are my oxidizer. So going back to this, I don't have water here. So ethanol is going to be my reducer. And then acetic acid and H plus. Well, I have acetic acid, I don't have H plus. This will be the conjugate oxidizer. And then over here, this is my oxidizer, gaining electrons. This must be the conjugate reducer. And so oxygen is my oxidizer, and H2O must be my reducer. So I'm going from stronger reducer, ethanol, to weaker reducer, water. And I'm going from a stronger oxidizer, O2, to weaker oxidizer, acetic acid. And so acetic acid is not on the oxide redox chart, nor is ethanol, but now we can place it. We know that ethanol is stronger than water. Where does it place exactly? We don't know. I mean, we'd have to do more experiments. All right, so now let's go back to HCl. We want to know the redox properties of HCl. HCl is H plus and Cl minus. So how should we do it? Should we do element plus element? What should we do? Single replacement? Skeleton? Chart? What should we do? And so over in this case, we're going to do the chart. Did I already do this? So, okay, what is H plus? Is H plus an oxidizer or reducer? H plus is an oxidizer. Here. If H plus got in a tug of war for electrons with H, who would win? H plus versus H in H2. Who would win? It would be a tie. So H plus, we need something weaker, or in other words, we need a stronger reducer than H2. What's a stronger reducer? Stronger reducer loses its electron more easily. So is lead a stronger reducer or H2S a stronger reducer than H2? What's the strongest reducer? Lithium, which is here. And so is lead stronger or H2S stronger? Lead is stronger. So if H plus, this is the zigzag method here, just like with the acid. If H plus reacted with lead, we'd go from H plus, this is our zig, and our zag would form lead 2. So if we go from H plus to lead 2 as a product, are we going downhill or uphill? Downhill in this case. We're going from a stronger oxidizer, H plus, to weaker oxidizer, lead 2. So we expect a reaction. And the other zag is here. We're going from H plus to H2. So if we're going from lead to hydrogen, it's weaker. So we're going from stronger to weaker. Stronger to weaker is favorable. So that would be downhill as well. And so what H plus can do is H plus can oxidize lead. Can H plus oxidize tin? If H plus oxidizes tin, it goes to tin 2. Tin 2 is weaker, so we're going from stronger to weaker. Can H plus oxidize iron? Yes. Zinc, aluminum, etc., etc. And so what we say is this. This is an oxidizing agent, and we will oxidize all reducing agents. Oxidizes all reducing agents stronger than H2. Okay, there are two ways of looking at chloride. Chloride's over here on the opposite side, and so chloride's not an oxidizer. Chloride would be a reducer. Okay, so one way of thinking about chloride is this. Is chlorine powerful enough to oxidize chloride? If chlorine and chloride got in a tug of war for electrons, who would win? It'd be a tie. So what we need is something stronger than chlorine. What's stronger than chlorine? Is PbO2 stronger than chlorine? Or is PbO2 is lead 4 oxide? Or is dichromate stronger than chlorine? Which one is what's the strongest oxidizer? Fluorine. So which one's stronger, chlorine or lead 4 oxide? Lead 4 oxide. And so it's going to be lead 4 oxide. And so, in other words, this. Lead 4 oxide, why do we even have it here? Lead 4 oxide is the oxidizer in car batteries, so that's why they put it here. And so lead 4, how many plus 4 cations do you know? Not that many, because they're pretty reactive. And so lead 4 oxide oxidizes chloride. What forms? Chlorine. So lead, this is our zig, that's our zag. So zig, zag. So chlorine is weaker. And so we're going from stronger to weaker. Is that downhill? Yes. That's in terms of oxidizing agents. In terms of reducing agents, this is the other way we'd say it. Chloride will reduce any oxidizer stronger than chlorine. And so here, looking at reducer agents, chloride will reduce lead 4 oxide to produce lead 2. And so chloride versus lead 2, chloride is stronger, lead 2 is weaker, so that's downhill. Do you see that? Except downhill on the right side is going up, downhill on the left side is going down. Probably should get rid of that terminology, like I said before, but I'm going to keep it. And so so there are two ways. Will chloride reduce lead 4? Yes. Will chloride reduce this? Yes. Or oxidize. I'd like to think in terms of oxidation. And so in terms of oxidation, is lead 4 oxide powerful enough? Yes. How about this permanganate? Is permanganate powerful to oxidize? Yes. Any of these. After permanganate comes hydrogen peroxide. After hydrogen peroxide comes, have you seen that before? You haven't seen that before because this is not common. What do you call Cr2O7 2 minus? Dichromate. Well, what is chromate though? CrO4. So something's wrong. If we have CrO4 and we have 2 of them, shouldn't that be Cr2O8? That's 2 chromates put together. Do you see that? Cr2O8. But it's not. Do you know what? Why? Because of this bond here. This bond is called a peroxide bond. Peroxide bonds are really unstable. So what happens is we get rid of one oxygen and put just a single oxygen link here. So it's a CrO-Cr. And so this is why it comes out to Cr2O7 rather than Cr2O8. This one looks like disulfate. Sulfate is SO4, 2 minus. So this is S2O8, 2 minus. That looks like disulfate, right?
Yeah.
But we don't call it disulfate. You know, this is not called disulfate because there's something weird going on here. One, why isn't it like dichromate? Shouldn't it be S2O7, 2 minus? And two, what's the oxidation state? Well, in dichromate, the oxidation state of chromium is +6. So we talked about +6 or chromium 6 earlier. What's the oxidation state on sulfur in this, which looks like disulfate? So if oxygen is -2, that's -2 times 8 is -16, -6, 16 plus, did you say +6? +7. So if it's +7, that's +4. Yeah, +7. But there's something weird about sulfur +7 because we know this. The normal range for sulfur is what? Yeah. If you look at sulfur on the periodic table, it's 16 total electrons. So we can go +2 electrons gets us 18, so it's -2 charge. Or we can lose 6 electrons. If we lose 6 electrons, we go to neon with 10 electrons. But if we go to +7, then that takes us all the way to past neon to fluorine. So if sulfur is +7, then that means it's isoelectronic with fluorine. Is fluorine very happy? No. And so you wouldn't imagine this to be very happy. But anyway, it turns out that's an unusual oxidation state. And that's the oxidation state you get, but in reality, that's not the true oxidation state of this. The true oxidation state of this, and it is a disulfate, is this. It's +6. We have the oxygens here. 6 of the oxygens are normal -2. 2 of these are -1. And so it's a peroxide bond. And so it turns out if we have a peroxide bond here, then we can maintain a +6 on the sulfurs. But if we have a peroxide bond here, is this very stable? No, it's not stable at all. And so this is why it's ranked number 3. It's ranked number 3 because it's so unstable. It's like a peroxide. Peroxide's number 4. This is number 3. And it's also a peroxide. And so this is not called disulfate. It's called peroxysulfate, peroxydisulfate, something like that. It has a very weird name. Okay, above that is what? O3, and then fluorine's at the top. And so what we have here is chloride will react with any oxidizer stronger than chlorine. Well, we don't have that many. Will chloride react with any oxidizer weaker? So let's say I try to get chloride. Let's say I try to oxidize chloride using dichromate. Am I going to be successful? No, dichromate's not powerful enough. And so what we can say is this. Chloride reacts with any oxidizer stronger than chlorine. When I say reacts, I can say reduces. Chloride reduces any oxidizer stronger than chlorine. So we've listed all the chemical properties of HCl. What are the chemical properties of HCl? We have the metathesis properties, we have the acid-base properties, and now we have the redox properties. And so we have a good idea of how HCl will react and the species that it will react with. And then we're done. So we'll get into some more practice with that later. Let's take a look at the lab for today. We're just going to start the lab right now. don't do the labs like they're written out. This is why I ask you to write everything in the lab notebook, because sometimes I don't follow the procedure as written. Right. We're doing lab 17. Uh-huh.
The lab report requires us to at least major and minor physics, but what do we use?
We'll talk about that. The lab report for this particular experiment will be a little bit different. Since I don't do things the same, and I do things different, semester to semester, you shouldn't, like if you see somebody who has a lab report from another class or another year, it's likely going to be different, a little different from what we do. So sometimes I get people, turning in work that they just copied off, somebody else who did it. But that doesn't work, because all the labs are going to be slightly different than what the other classes are doing. But let's go ahead and continue. For right now, we'll just continue as it's written. So we did we do distilled water? Actually, no, we didn't do distilled water. We didn't have any distilled water was too expensive for us. So we used instead a much cheaper deionized water. So that's one difference there. It's not distilled, it's deionized. Did we do tap water? Did tap water conduct very well? Would you say it was a weak, strong, or non-conductor of electricity? Well, it's relative. I mean, it's strong. You can electrocute yourself and kill yourself, by electrocution. But compare that with ocean water. What do you think would conduct electricity better, ocean water or tap water? Ocean water. And so if ocean water were strong, then tap water would be weak. And so tap water is a weak conductor of electricity, but still plenty powerful enough to electrocute you. And so what should you say about major species and minor species? Do you know what's in tap water? Not really, except dissolved minerals. Those minerals are salts. So what we say is there are some salts dissolved in water. Can you taste them? Can you taste this? Does tap water taste salty to you? Probably not. Tap water, I can't taste the salt in tap water. Can you taste the salt in ocean water? Yeah, definitely there, no problem. But tap water, there's got to be salts dissolved in there, because that's what's conducting the electricity. If we have salts dissolved in water, we call those soluble salts. Now, are soluble salts strong electrolytes, weak electrolytes, or non-electrolytes? Strong electrolytes. But strong electrolytes should strongly conduct, but tap water weakly conducted. And so this is what we say, because conductivity depends on three things. What are the three things conductivity depends on? Number, mobility, charge. So tap water is a weak conductor of electricity because the number, it's not that concentrated, the salt. And so we can say different things. We have two ways of defining electrolyte. If you're a battery person or into electrical circuits and whatever else, you'd say it's weak. It's a weak electrolyte. But it's a weak electrolyte because it doesn't conduct electricity very well. But for us, we're going to call it strong electrolyte because they're soluble salts. Soluble salts is strong electrolyte. But what we're going to say is that they're in low concentration. Since they're low concentration, it's going to give us a weaker conductivity. And so strong electrolytes, but low concentration. You can't even detect it with your tongue. Maybe you can, because you can taste the minerals, probably. You know, they give some kind of flavor to it, I think.
What's like with the DI?
GI water would be a non-electrolyte. We call it a non-electrolyte because it didn't conduct, but in reality, it's a weak electrolyte because it partially ionizes. Remember I talked about that? And so I'm being inconsistent with my definition. But that's the problem because of these two definitions, and then there's a cutoff, you know. So it's all right. It's a non-electrolyte because it doesn't conduct any electricity at all. And so it's just putting it into perspective. All right, what's next? Solid sodium chloride. So I have it here, table saw. Let me just check to make sure this is still working. So I have a piece of graphite here. Graphite conducts electricity via electrons. And so electrons are moving through the graphite here. But these salts conduct electricity by ions. The charge carrier is different. Do you see any? No, it's non-conductor. Why is it a non-conductor? Isn't sodium chloride, you know, when people say get your electrolytes, isn't this an electrolyte? Good electrolyte, good strong electrolyte? It is, but, you know, we have ions. We have sodium ions and chloride ions. So we have plenty of ions. So N is big, E is big, +1, -1. What's wrong? No mobility, right? The ions can't move. We need translational motion. And the ions are locked in a lattice. They only have vibrational motion. So what's one way of freeing up the ions? Dissolve it. So as we say sodium chloride is a good strong electrolyte because when you dissolve it in water, it breaks up into ions. There you go. So it lights it up quite nicely. So it's nice and bright. Okay, the other way of freeing up the ions is by melting it. Okay, what's next? KClO3 solid. Sodium chloride is hard to melt. The melting point of sodium chloride is around over 800 degrees C. KClO3 has a much lower melting point. But KClO3 I have to be careful with because when we think of chloride, is chloride very reactive? Chloride's not very reactive. Chloride metathesis, tell me what chloride reacts with in metathesis reactions. Silver, lead, mercury, lead 2, mercury 1, good. In acid base, tell me what chloride reacts with. Anything stronger than HCl, but remember the leveling effect? So nothing. Chloride reacts with pretty much nothing, and therefore in water it's neutral, unreactive. And this means this. What it means is if you ran out of antacid and you have some sodium chloride, could you use the sodium chloride to neutralize your stomach acid? No, because chloride is neutral as a base. It's really ineffective. But chlorate, on the other hand, chlorates, what is it, nitrates, acetates, and chlorates are all, nitrates, acetates, and chlorates are all soluble. So for metathesis, no reaction. You know, chlorates are not going to precipitate out with anything, basically. It's not going to form a gas. And chlorates are about as basic as chloride. Remember, chlorates are from chloric acid. And so chlorates have no metathesis properties and no acid-base properties. And therefore, are they totally unreactive? No, because did we consider, what other properties do we need to consider? We consider metathesis, acid-base, we need to consider redox. And so chlorate, is it on our redox chart? Good. Chlorate's not on our redox chart, so we're safe, right? You don't have to worry about chlorate because it's not on the redox chart. Is that right? No, because our redox chart's not comprehensive. I could look in, there's a more comprehensive redox chart in Appendix D of our book. But do you see something similar to chlorate? I see iodate. And iodate is a pretty decent, what? Iodate is a pretty decent oxidizer. If iodate's a pretty decent oxidizer, what do you think chlorate is? A pretty decent oxidizer. And what do you think? Do you think it's a more powerful oxidizer than iodate or a weaker oxidizer than iodate? More powerful, yeah. I'd expect this to be more powerful. Both chlorate and iodate have the same oxidation state. What is it on chlorine here? +5. Is that a happy chlorine atom or an unhappy? That's an unhappy chlorine atom. And so I want to be careful with this stuff because this stuff is a strong oxidizer. And I want to avoid mixing this with reducers because I could have a violent reaction take place. So I'm going to wear my goggles for this one. And I'm going to be careful with this. I'll take a scoop and scoop out some potassium chloride. Potassium chloride is just this white solid. Do you expect it to conduct electricity? No. I got to watch out what's on the electrodes here. I got to make sure there's no reducers on there. Otherwise, I might have a reaction, unwanted reaction. But do you see anything? No. Okay. So what do you call it? Well, it didn't conduct electricity. It didn't conduct electricity because it was missing what? Mobility. There's no mobility. There are plenty of ions. Just no mobility. So we got mobility with the sodium chloride by dissolving it in water. We're going to get mobility with the potassium chloride by melting it. And so if I melt it, what's going to happen is it's going to break all the ionic bonds, and then I'm going to have molten potassium chloride. The potassium chloride solid, and then do you know what the symbol for heat is? Delta. And then I'm going to melt it. And so I'll get potassium chlorate liquid. Potassium chlorate liquid is going to consist of mobile potassium ions in the liquid state plus mobile chlorine ions in the liquid state. When I have molten potassium chlorate, I want to be careful because of this. I used to demo this. I used to put like paper towel in here But other people, depends on how much you get. There's a very common demo where people take gummy bears and throw the gummy bears in molten potassium chlorate, and they just go up in a big flame. But the smoke detectors here are too sensitive, so I stopped doing it. I got to make sure there's no reducing agents here. Maybe I'll try a wood splint. That might be interesting. So the way we do it is Bunsen burners you can hold in your hand. This way, if things start to get out of control, you can remove the heat quickly. So let me try to melt this stuff. Do you hear that? Maybe there is something in. You got to be careful because if you throw a gummy bear there, you could have a fireball come back and hit you in the face. I wouldn't want to do it. There could be something in there because you got to worry also, because when you take things like chlorate, you can make nasty gases from this if there are reducers in there. Copper is a good reducer too. These electrodes are made out of copper. And so I smell some nasty gas coming off this. That was probably the noise. Hopefully it's not too much. One of those gases is phosgene gas. Phosgene gas was actually this is not deep enough. So it's melted. Potassium chlorate has a low melting point. I need to raise this up a little bit. There it goes. I didn't have enough there. So that's molten potassium chlorate. And so you can make gases that are worse than chlorine. I want to solidify it, so I'm going to cool it down. But the way I'm going to cool it down, I'm going to spray water on the outside of this, but you have to watch out for thermal shock. But these ceramic things are pretty good with thermal shock. All right, it's not getting cool enough. Do you know why? Because with the electric current there, it's keeping things hot, molten. So what I'm going to do is I'm going to unplug this and then cool it down.
Is it not just gonna, get it stuck on the electrodes?
It's stuck on the electrodes right now.
You gotta clean it off.
Yeah, I got to clean it off. All right, so I plugged it back in. It's solidified. Do we see any electrical conduction? No, but these electrodes are really easy to clean off because potassium chlorate is group 1 salt. Group 1 salts are soluble. So, I'm just going to wash it off here, the electrodes. But when I wash it off, the group 1 salts dissolve, and group 1 salts are strong electrolytes, basically. And so this is the other way of freeing up the ions. So this is a potassium chlorate aqueous. Yeah. The liquid, potassium chlorate liquid was the molten stuff, the hot. This I cooled down, it's solidified, now it's just aqueous. Aqueous potassium chlorate is going to consist of potassium ions aqueous and chloride ions aqueous. And those aqueous ions can conduct electricity. This is called ionic conduction versus electronic conduction. So one of the pieces of copper here is positive, the other piece of copper is negative. This is the AC current, so it's a little bit different. And so the positive will be the chlorine ions will travel to those, and the negative, the potassium ions, will travel to those. And so this is how it's conducting electricity, the transport of ions, rather than the transport of electrons. I didn't manage to dissolve all of it, so I'm going to drop this down. Here. You can see some potassium chlorate. The potassium chlorate's been discolored. There's some black on here. That black is from the electrodes. The electrodes are so dirty. See that? Okay, let's put that. Okay, what's next? Copper 2 sulfate or copper 1 sulfate? Copper 2. Copper 2 sulfate. Copper 2 is much more common. Copper 1 salts are rare. Most of the copper salts that we deal with are copper 2. This is copper 2 sulfate. Copper 2 is what color? Blue. Sulfate's colorless. And so, should I take the bottle and put it up in here? No, because these electrodes are dirty. I'm going to contaminate my copper 2 sulfate. And so, proper technique is we don't want to contaminate our source. And so we'll transfer it into a beaker, and then a small amount into a beaker, and then just test that. So soluble salts with strong electrolytes. Strong electrolytes are going to break apart. So we should have copper 2 ions and sulfate ions. We'll plug it in. So it's a strong conductor of electricity. And it's a strong electrolyte. Copper 2 and sulfate ions. Okay, do I want to pour this back in here? No, if I pour it back, then it's just contaminated. I don't want to do that. You pick glasses up by the label side. The label side. That way all the spills are on one side. But if you look at the lead bottle says spills all the way around it, 360. So some people don't follow the rules. What's next? Liquid ethanol. This is not aqueous. This is liquid. Liquid ethanol is pure ethanol. Pure ethanol is 100% ethanol. Do you know what proof 100% ethanol is? This is 200 proof. 200 proof. When you smell chemicals, don't hold it underneath your nose. Instead, waft the vapors. It smells like ethanol. Probably tastes like ethanol. Have you ever tasted 200 proof alcohol? No. It'll just evaporate off your tongue really quick. But if you take a shot of this, what happens is most of it evaporates into air. You lose a lot of the alcohol, unfortunately. It just evaporates so fast, Don't sneak a drink of this. Actually, it's not a bad idea to try it, but you don't want this to drink this because this is denatured. It's they put some kind of carcinogenic, mutagenic contaminant in here to prevent people from drinking this. So it's no fun. But the reason they do that is you don't have to pay consumption tax on this. And so, so this is not for consumption. So we can test the ethanol, but I don't want to dip it in here, otherwise it's going to contaminate. Which I did. I did that this morning. And It was contaminated, but it should still be okay, I think. Just in a rush. So ethanol conduct? No. The reason it's denatured is that's how it's made. When you distill alcohol, do you know how pure you can get it? You can get it to 95%. 95% is 180 proof. So you can get 180 proof alcohol by distillation. That last 5% you can't. And so what they use is I think, methylene chloride to extract the remaining 5% of the water. And the methylene chloride is mutagenic and carcinogenic. Okay, but this doesn't conduct. And then we try aqueous. So if I add water to this, will it conduct? What do you think? No. It still doesn't conduct, even aqueous ethanol. All right, we're out of time though, so I'm going to stop here. We'll just continue this on Wednesday. Yeah, because it's too hard to remove the little tiny bit of residual. They use that to extract the water, and so it's too, and so it ends up being contaminated a little bit. Just in the process of making it. I know. It'd be nice to try. But, lots of people drink 95%, 180 proof. You can buy it at different places. Like, they call it like Everclear or something. Just close.
I'm going to do it myself. I want to see something.
Office hours right now?
Yeah. So if you have questions, I'm sticking around. So I have office now, so if you guys have any questions.